Dear student, today we'll start uh, actually lattice dynamics. Lattice dynamics means that the particles, atoms, like they are arranged in a periodic array, and when wave pass through this crystal, the propagation of wave, how it will behave, it depends on the position of atoms in the lattice, because when wave pass through the lattice, then atoms in the position, individual position, they start to vibrate. And this vibration is coupled vibration. I mean, say one atom in a position is linked with just spring-like with another atom. So the effect of adjacent atoms, even little bit nearby atom, will have some effect on the vibration of the atom, and that vibration and wave propagation uh, will be something different. To study this, we will start in one dimension array. Say so this is one dimension array of atoms. One can see here the red color circles, these are atoms. They're linked with spring like elastic they're linked, and you can see that the position of a particle, say at nth position, and its displacement, say un. If you go through right side, the position of next atom in a position, say x, it has displacement un plus 1, and next atom is un plus 2, and so on. If you go left, then the displacement of the atom is un minus 1, and next left atom with un minus 2, and so on. So this is the arrangement. When wave pass through this array, if you consider nth position atom, it will vibrate, but due to elastic combination, it will be affected by other nearby atoms also. How they get affected, that we'll study. So in that case, we consider one monoatomic linear chain here. We consider the atom at x position with its displacement un at a particular time, and the right hand side adjacent atom with displacement un plus 1, and left hand side atom with displacement un minus 1. So expands the energy near the equilibrium point for the nth atom, use elastic approximation, then equation of motion becomes the force to the right is un plus 1 minus un, where the displacement of n plus 1th atom is un plus 1, and displacement of nth atom is un. So the difference in their displacement un plus 1 minus un will be the distortion due to the right hand side atom. Similarly, the force to the left due to distortion un minus un minus 1. So these are two distortion due to right hand side atom and due to left hand side atom. The force will be proportional to this distortion. From the elastic properties we can write this. So total force will be force to the right minus force to the left. If it is so, then the equation of motion will be mass of the nth atom m u double dot n, where double dot is the derivative of displacement of the nth atom with respect to time t. So this is the force acting on the nth atom. As per the elastic law, this should be equal to some constant into the total distortion due to left atom and right atom, which you can see here un plus 1 minus 2 un plus un minus 1. Actually, we have added two terms. One term comes from right side, one term comes from left side. So this is the equation of motion for this atom at nth position. Next, we assume here that the displacement of nth atom with time t is given by a constant exponential ikx minus omega t, which is standard wave equation. X is the position of the atom and omega is the frequency of vibration at time t. So this is the displacement at time t of the nth atom from the equilibrium position un. Similarly, where we have taken x equal to na, quite understandable, I think, where a is the interatomic distance. Since we consider this as nth atom, so total n number of interatomic distance a is there. So we consider here the position of the nth atom as Na. So this is the expression for the displacement from equilibrium for the nth atom. Now, similarly, we can just simplify this. It is simple from the first expression to second expression. We come here, we put the value of x as Na. So the same expression for nth atom, the position displacement of the nth atoms from equilibrium position. So the expression for u dot n is del un del t, and if you put the value of un here and go for derivative, then we get the u dot n as I a omega exponential I k n a minus omega t. I think you understand this. Simple derivative is here, and double derivative will be again, if you go for derivative, it becomes minus a omega square exponential I k n a minus omega t. So then we put this in the equation. Already we established the equation of motion. Mu double dot is equal to alpha un plus 1 minus 2 un plus un minus 1. Put the value here. So if you put the value here, already we expressed un double dot as a omega square exponential. Put here in the left hand side, and right hand side you put the value of displacement of three atoms, one for n plus 1th atom, second is for nth atom, and third one is n minus 1th atom. So you put here in the standard wave equation, then we get this expression. So if it It looks very big, just derivation, but not so big. Only we have put here the value of u and double dot and the n and n plus 1 and n minus 1 atoms displacement only put here. Then if you go for simplification, this can be written as just the first term I am explaining you. Inside you can see k into n plus 1 into a. So if you simplify this, so one term will be I k n a and other term will be e to the power I k. That I have written in the right side into e to the power I k a. Similarly, second expression and third expression. In third expression, you can see it was n minus 1. So if we simplify this, the product term will be coming exponential minus IKA. So this is the simplification of the expression from the uh, equation of motion. Then we get, if you just cancel the term, exponential term in the both sides, that is exponential e to the power I k n a minus omega t. If you cancel in the both sides, then we get minus omega square m in the left hand side, and in the right hand side alpha within bracket e to the power I k a plus e to the power minus I k a minus 2, where alpha is the spin constant, that is coupling constant between two atoms. So it is simplified form of the equation of motion. Here we see that omega square has come, where omega is the frequency of vibration. So omega, the frequency of vibration, is related to the spin constant or elastic constant between two atoms alpha and depends on the wave vector k. A is the interatomic distance and m is the mass of the atom. So these are constant. So basically we get here a relation between frequency omega and the wave vector k. So this is one equation relating frequency versus wave vector. This type of relation is known as a dispersive relation. Means this relation gives us the value of frequency with which the system of atoms will vibrate, omega, and it is a function of wave vector k, where k is 2 pi by lambda, the wave vector. So ultimately we get, if you put the exponential IKA plus exponential minus IKA with the help of de Moivre's theorem, then one can see very easily exponential IKA plus exponential minus IKA as twice cos Ka. So the expression, the dispersive expression, comes as minus omega square m is equal to alpha within bracket 2 cos Ka minus 2. Now, if you take 2 as constant, the same expression looks like this: omega square m equal to twice alpha 1 minus cos Ka. So this is the expression for frequency omega, and after simplification we see that 1 minus cos 2 theta, you know the formula, that is 2 sine square. You know the formula, 1 minus cos theta is equal to 2 sine square theta by 2. The same thing we have written here. In the right hand side, we have written 2 sine square Ka by 2. So then finally we get omega square m is equal to 4 alpha sine square Ka by 2. So this is the relation between frequency omega and wave vector k. So this is dispersive relation. So we get ultimately omega square equal to 4 alpha by m sine square Ka by 2, or omega equal to, we get plus minus square root 4 alpha by m sine Ka by 2. Now what is physical interpretation? What is omega? Omega is the frequency of the vibration with which wave propagates through the area of atoms. And this frequency is related to basically the wave vector. So here omega is a function of k, or the frequency is a function of wave vector k. And obviously this relation depends on two things. One is the spin constant alpha, and other is the mass of the atom. This relation is known as dispersive relation of omega with k. So finally we get, if we put square root 4 alpha by m as the maximum frequency omega naught, the relation dispersive relation is given by omega equal to plus minus omega naught sine Ka by 2. So this relation is the dispersive relation which describes the variation of frequency with wave vector. Means that if you know the wavelength of the wave propagation, then what will be, or if you know the wave vector in different direction also, then you can determine with which frequency it will propagate through. So this is known as dispersive relation. Next comes the variation of omega with wave vector k. How we get this? It is simply depending on the dispersive relation. Already you can see here omega is equal to omega naught sine Ka by 2. It means that basically this will be some kind of uh, sinusoidal K by 2 curve. That is sub-angle sine curve will be here. This curve only plotted in the figure you can see. So here the variation between frequency omega and wave vector k. Now some very important point you can observe from this variation. At wave vector k equal to 0, that means if you come the symmetry direction there, the frequency is 0. There is no frequency. That means there is no any wave in this direction. If you go the value of k towards positive direction at a point k equal to pi by a, means when wave vector is reciprocal of a as pi by a, at this point the frequency is maximum, that is omega naught, which is given by square root 4 alpha by m. Similarly, in negative direction, if you go k value minus pi by a, there also omega will be maximum with the value square root 4 alpha by m. So maximum frequency one can see, one can understand depending on the coupling constant, spin coupling constant alpha, and the mass of the atom. So if mass is more, m is more, means that atom is very heavy atom. In that case, the frequency, maximum frequency is very less. So for that atom, the vibration is very slow and frequency is very less also. And if we see the elastic nature of the chain of the atoms, if alpha is more, what is alpha? Alpha is the spin coupling constant alpha. Means that if adjacent atoms are very tightly close to the atom, alpha is more, then only the frequency, maximum frequency of vibration will be more. One thing you should remember that here we are talking about which wave that is generated due to the vibration of the lattice points, or it is generated due to the vibration of atoms in the array. So as a whole, this is the vibration of lattice, or this wave is due to the lattice vibration. Lattice vibration means the component of lattice is vibrating, they are not at rest. So this is lattice dynamics. Due to this lattice dynamics, wave is generated and frequency you can find from here. This type of vibration sometimes also known as phonon vibration. And later on we will see that this phonon vibration can be also quantized, known as phonon particle. So this phonon vibration having maximum frequency, which depends on the spin constant alpha and which depends on the mass of the atom. Next we'll go the phase velocity. What is phase velocity? Already you know, when some wave, individual wave, pass through the medium, then we can find the motion of a constant phase. Means that if you talk about a single wave, then and if you consider particular phase on the wave, after some time, that constant phase will be shifted to another point in the space. So one can say that a constant phase also is moving forward. With which velocity this constant phase is moving is known as phase velocity. And it is given by the ratio of frequency omega and wave vector k. So we get from this relation, we know the value of omega. Put here for this monoatomic chain lattice, the omega is given by square root 4 alpha by m sin ka by 2 by k. After some modification, you can write this phase velocity as square root 4 alpha by m into sine ka by 2 by k. So this is the expression for phase velocity. So if you know the variation of phase velocity, simple just you plot this graph, means that phase velocity is basically 1 sine theta by theta form. Because here theta is variable, means k is variable. So you should consider this as the sine theta by theta form. And sine theta by theta form, you know already this variation can be given like this. One wave in nature peak will come and then peak will go slow down. And obviously here we can see this. And here we see that the phase velocity also maximum in the very symmetric direction where the wave vector is 0. Here we find that phase velocity is maximum with a value you can find from here with the phase velocity, maximum phase velocity. That is, you can give here k by 2, the 2 by a. So 2 by a squared 4 alpha by m. This will be the maximum phase velocity, which is represented by a peak at point k equal to 0. So here we get the maximum phase velocity. And if you go the reciprocal lattice, then for the k value pi by a, here you can find the value is approximately 0.665 value of maximum velocity, maximum phase velocity. And when you reach the k vector at 2 pi by a, there you can find the phase velocity is 0. So this is the variation of the phase velocity with k vector. Now already you know that this region from minus pi by a to plus pi by a is known as first Brillouin zone. In the first Brillouin zone, you can find very good variation of the phase velocity taking the maximum value of phase velocity at very symmetric position k equal to 0. And the region that is from k equal to pi by a to 2 pi by a, and in left hand side in minus pi by a to minus 2 pi by a, this region is known as second Brillouin zone. Here you can see the phase velocity is decreasing with increasing in k value. So this is the variation of phase velocity with respect to uh, k value. Okay. And next we'll go, what is group velocity? Group velocity basically, you can see group velocity here. It is given by d omega dk. So if you go for the derivation, you differentiate the expression for omega. In simple differentiation, it comes as a by 2 and then square root 4 alpha by m. Sine becomes cosine. This is the expression for group velocity. So for group velocity, you see that it is not the sink curve. What was seen in case of phase velocity? Sink curve. Sink curve means sine theta by theta form. So somewhere you will be finding the maximum velocity, maximum value, and then it will be diminishing with also diminished amplitude also. But here we get the perfect cosine of sub angle. So it is not diminishing like this. So in that case, we expect that the variation of group velocity will be something like this. So you see that each and every position, the amplitude of the variation of group velocity is constant, and that is given by a by 2 square root 4 alpha by m. So this is group velocity. So you see that also group velocity is maximum in the symmetry point where k equal to 0, and then in the first Brillouin zone, at the end of the first Brillouin zone, it comes down to 0, 0, yes, where k equal to plus pi by a in the right hand side and k equal to minus pi by a in the left hand side. So we get in the first Brillouin zone the variation of group velocity as a function of cosine of subangle, because you see here ka by 2, not simple ka. So that's why I'm telling this is cosine of subangle. So you see the variation of group velocity will be just like this. So we get two variation here. One is the phase velocity and one is the group velocity. Again, I'm telling what is the relevance of this kind of phase velocity and group velocity here in lattice dynamics. I told you that lattice dynamics is nothing but the vibration of lattice as a whole. And due to this vibration, wave will be generated and phonon vibration will be there. So phonon wave will go through the lattice due to this lattice dynamics. And with this phonon wave, there will be two velocity. One is phase velocity of the phonon and other is group velocity of phonon. Now, what is phase velocity? We see here that actually this phonon wave will be a combination of many of individual wave, and the phase velocity is the constant phase movement for individual wave, and the group velocity as a whole when it will combination of all individual waves, then the velocity of the phonon as a whole will be group velocity, and it is given by a by 2 square root 4 alpha by m cosine k by 2. So this is the variation of phase velocity and group velocity. Next comes, let's see what will be the real value. One example will be giving here that what is the group velocity value. Already we have seen here that group velocity v is equal to omega naught a by 2, where omega naught is that one, where omega naught is basically square root 4 alpha by m. So omega naught is square root 4 alpha by m, and then a by 2. So the expression for group velocity is omega naught a by 2 cosine k by 2. So let's see one example we are taking on extreme case. Extreme case, if we talk about k equal to 0. Now, what is meaning of k equal to 0? K equal to 0 means lambda will be what? Infinity. So if you take very long wavelength, if you take very long wavelength, for this long wavelength, sufficiently we can consider k tends to 0. If k tends to 0, then already we know that cos 0 almost 1. So we get, sorry, cos theta, when theta tends to 0, then generally we get, yes, we get the expression for omega naught ka by 2. Omega naught ka by 2. Okay, so omega is like this. So, and we see that in this limit, both are equal. Uh, both are equal. In that sense, the phase velocity and group velocity will be omega naught a by 2. So we get then. Sorry, please. You just revise this. Omega tends to what I written is not proper. Omega naught k by 2. It should be omega naught a by 2. Because k when tends to 0, then cosine part will be 1. Then the expression for group velocity will be simple omega naught a by 2. So we see that the expression when k tends to 0, group velocity is omega naught a by 2. What about phase velocity? You can see the expression of phase velocity. It is also will be omega naught a by 2 also. Okay. So this is the expression for group velocity and phase velocity in the limiting condition when lambda is very high, wavelength is very big, means k almost 0. So we get the phase velocity and group velocity same, having a value omega naught a by 2. Now omega naught is the maximum frequency and a is the interatomic distance. So here we can have one idea that both the velocity with which the phonon wave will propagate is half of omega naught a, half of omega naught a. Okay, uh, one can remember in case of plane wave propagation, it is basically omega naught a. Here it is half of that. So we get one difference in normal wave where the maximum velocity is omega naught a. Here we get the maximum velocity in the limit of very long wavelength, that both the phase velocity and group velocity is omega naught a by 2. So again, one point here, you see that the phase velocity or group velocity depends on the interatomic distance. If interatomic distance is more, then we see that here the phase velocity and group velocity is more. But at the same time, it looks like this. But at the same time, if you see omega naught, it depends on the spin constant alpha also. So we can say that this phase velocity or group velocity, depending on two terms, one is the interatomic distance A and other is the maximum frequency. So this is the value of the group velocity and phase velocity at this limiting point. Let have some example. Say, for example, if you consider normal sound velocity, then Vp is of the order of 10 to the 3 meter per second, and A, if you take approximately 10 to the minus 10 meter, what is in reality in the lattice, the interatomic distance. If you put the value here, then one can find that omega naught is coming almost 10 to the 13 radian per second. Means that in this relation, if you put the phase velocity as 1000 meter per second and a put as 1 angstrom unit, that is 10 to the minus 10 meter, then omega naught will come as 10 to the 13 radian per second, which is in the range of terahertz or in the infrared range. So one can have some idea that due to the lattice vibration or lattice dynamics, uh, the wave in the infrared range will propagate with a frequency of the order of 10 to the 13 that just exist in the range of terahertz. So we get some terahertz wave propagation through the lattice vibration in this case. So this is actually today's discussion, that today we discussed first what do we mean by lattice dynamics or lattice vibration. We explained that lattice vibration is the periodic array of atoms which are in the lattice. They will vibrate, but they will vibrate around their stable position, and this vibration will create as a whole a wave generation in the lattice. This vibration due to lattice dynamics is known as phonon vibration, and the wave which is generated due to this lattice vibration is a combination of phonon wave propagation. Now, at the beginning, we have taken very simplified form. We consider one dimension array of atoms. They are arranged in a periodic way with some interatomic distance, some specific interatomic distance, and then we see applying the mechanical law and also the elastic properties, and taking consider the nearby atom only with elastic property, then we see that the frequency maintains a dispersive relation with k wave vector. This is known as frequency dispersive relation with lambda or wavelengths. And there we have seen that this maintains some kind of sinusoidal variation of sub angle, and we see there that the omega, the phonon vibration is maximum at a value for k equal to pi by a. In this region where k equal to minus pi by a to plus pi by a, which is known as first Brillouin zone, here we see that with the increase in the value of k, the phonon vibration or frequency will increase and will reach a maximum value where the k is pi by a. Next, we discuss that due to this phonon vibration, we get two types of velocity. One is phase velocity, which relates to some individual phase, and we get the group velocity, which is a combination of many of such kind of vibrations. Then we find two velocities. One is phase velocity and other is group velocity. And then we see that at the extreme case, when we go the very long wavelength where k equal to 0 tends to 0, then we see that both of phase velocity and group velocity becomes equal with the value of product of maximum frequency into a by 2, which is half of approximately of that maximum velocity what is found in case of normal wave propagation. Now we have an idea. We see that This just vibration fall in the range of terahertz vibration. So this was the discussion today, and we have completed the vibration, phonon vibration in single chain of atom in one array. This is today's discussion. Next we'll be taking diatomic system. Today we have taken monoatomic system. We'll be taking diatomic system, two atoms, different atoms, and how they just mediate this kind of dispersive relation there we will discuss. So this is today discussion. Thank you very much for your kind listening and also understanding. Further, if you have any queries, you can just ask me. I'll be able to answer you and clear you. Thank you very much. Have a nice day.